In this video, we'll talk about Bézout's identity and how to derive the coefficients that it refers to. Bézout's identity is related to greatest common divisors. And in this case, if we wanted to find the greatest common divisor of 310 and 710, we would use the Euclidean algorithm to generate these successive equations that you see on the screen here. If you'd like to watch that video and learn where these equations came from, click on the link you see on the screen. Notice that I've colored in the dividend, the divisor, and the remainder in each of these equations. Remember when we talked about the division algorithm that those are the numbers that get copied to the left as we go through each equation. Notice that in the first equation we have a remainder of 90, and then that remainder becomes the divisor, and then that divisor becomes the dividend. So that it's the same 90 each time, and so the color coding is going to help us as we work through Bézout's identity. So what is Bézout's identity? Well, notice at the top of the screen now the problem has changed. Now we want to find integers u and v such that u times 310 plus v times 710 equals the GCD. And those are the coefficients that are guaranteed to exist by Bézout's identity. So Bézout's identity says that we will always be able to find numbers like that. If I replaced 310 and 710 with two completely different numbers, I would still be able to find integers u and v such that u times the first number plus v times the second number equals the GCD of those two numbers. And the way that I do that is by starting with the equations that I get from finding the GCD in the first place. So these four equations that you see on the side of the screen here, we need to do that anyway. So even if you knew what the GCD was, we would still need these equations, as you'll see in a second. Okay, so we know our GCD is 10. And what we'd like is an equation that looks like 10 equals u times 310 plus v times 710. Well, we can't get that right away. But what we can get easily is an equation that looks like 10 equals something times 40 plus something times 90. And we can get that from this next to last equation. So if I solve that equation for the 10, which I'm just going to do by subtracting 2 times 40 from both sides, I'm going to get the equation 90 minus 2 times 40. But I'm going to rewrite that slightly just to make it a little bit easier to work with. I want to make this look like the kind of equation that I want, which is a number times 90 plus some other number times 40. So just rewrite it slightly and write this as 1 times 90 plus negative 2 times 40. And notice that I'm keeping the color coding here. So if you'd like to follow along and do this with lots of fancy colored pens, that's okay. What some students will do is you'll write the numbers in boxes, or put a circle around one and a star around another, or a cloud around another. So somehow indicate that the 90 and the 40 are much more important here than the 1 and the negative 2. The 90 and the 40 need to be kept as 90s and 40s. I don't want to write this equation as, say, 90 minus 80, because while 2 times 40 is certainly 80, I want to keep that 40 there for a reason that you'll see in just a second. So we sort of have what we want. We have 10, the GCD, equaling something times 90 plus something times 40. But I don't want it to be 90 and 40. I want it to be 310 and 710. So how do I get closer to what I want? Well, now I want to use the next equation in line. So the next equation tells me how to rewrite 40. So I'm going to replace the 40 in my equation with what I get by solving this equation, the second equation in my line. I'm going to solve that equation for 40 and plug what I get in for the 40 that I have over here. So let's do that. So we still have 1 times 90. And we still have plus negative 2 times, but now the thing that negative 2 is being multiplied by is what I get by solving that second equation for 40, which is 310 minus 3 times 90. So 310 minus 3 times 90. Now I want to simplify this expression here, but I want to keep the 90s and the 310s as 90s and 310s. So I still have 1 times 90, but now I'm going to distribute my negative 2. So I have plus negative 2 times 310 plus, now I have negative 2 times negative 3 times 90. So that's 6 times 90. And now I have one 90 and 6 more 90s, that makes 7 90s. So I have 7 times 90 plus negative 2 times 310. Alright, so now notice that I'm closer to what I want. I want u times 310 plus v times 710. So I have something times 310, that's good. But I have this 90 here, and I'd really rather have something with 710 in it. So what I can do is use my first equation. So my first equation, if I solve that first equation for 90, that gives me an expression for 90 involving 7 tens and 3 tens. So I can rewrite this equation as 7 times, not 90 anymore, but I'm going to rewrite 90 as 710 minus 2 times 310. And then I still have plus negative 2 times 310. So when I distribute this, I get 7 times 710 minus 14 times 310 plus negative 2 times 310. And I'm almost done. All I have to do is collect together the 3 tens that I have in 2 different places there. So I have 7 times 710 minus 16, or plus negative 16, times 310. And that's what I wanted. So this final expression down here is what I wanted for Bézout's identity. So this process is called back substitution. And notice that at each stage we were substituting using one of the equations that we had from our division algorithm. At the very beginning, we had our expression for our GCD in terms of 90s and 40s. And then we substituted for the 40, and then we had an expression in terms of 90s and 310s. And then we substituted for the 90, and then we finally had what we wanted, an expression in terms of 7 tens and 3 tens.